Thank you very much. Thank you very much for the opportunity and the nice introduction. My topic of today's talk is we will be discussing modeling nanomaterials for CO2 conversion, and we will be specifically highlighting how you can identify the markers uh, who can give you insights whether CO2 is activated or not. And we'll be discussing various materials, specifically 2D materials and metal oxides in this particular lecture. Before I go into the technical details of the first principle-based simulation that our group is working on, I'll be first motivating you the application point of view, which is in this talk we'll be discussing mainly on the CO2 capture and conversion, which is towards CCUS, and we are providing computational insights into designing new materials for this very application. So if you look at the energy consumption in different industries, as well as the transport, residential, commercial, and any kind of other areas, you will see that industries are the major total energy consumptions. And among the various industries, the chemical industry is one of the main industry where this it is we can call it energy intensive industry actually. So this is the second largest industry energy consumer, and the reason is that because it uses fossil fuels both as a raw materials as well as and fuel, and accounting about 14% of the total industrial energy consumption. So people are moving towards the replacement of the fossil fuel consumption by renewable energy, and in particular in chemical industry, this is a central strategy for resource and energy efficiency. So if we just have a broad picture of a pre-industrial environment and how the things have changed nowadays, and that has caused increase in substantial increase in the CO2 in the environment from 80 ppm in 1950 to about 426 ppm in this 2024, and it's increasing day by day. So initially, the focus, as I have tried to highlight in a very simple manner, is was on CCS. It has some potential issues, and you can have a potential leakage, huge energy consumption was required. And this on the right side, we are showing here that what are different techniques to capture the CO2, and then we'll be showing you the different traditional materials that people have been using in this field. So basically, CO2 reduction, which is actually the utilization of CO2, converting CO2 into some useful chemical by either hybridization or converting CO2 into the carbon monoxide. People have been using different materials, as I said, that metal organic frameworks, ionic liquids, even metallic clusters, amine-based systems for the capturing of CO2 first, and then converting them into chemicals. So it's a three-step process. You have to capture it, separate. There are issues in separation of in the gases, flue gases and all, and then you have to store and utilize it. So this is how the whole picture looks like in the case of CCUS. So if one has to briefly state what is carbon capture, utilization, and storage CCUS, it's first is the capturing of CO2 from whatever sources you have in the industries uh, or by any other means. And then, if not being used on that particular site, you have to capture, compress it, and transport it by pipeline. That can involve some issues, as I said, of leaking and all. So here comes the role of catalyst development, and the challenges the industry is facing. And basically, if in one line we have to specify this, these reactions are designed to run at low temperature and pressure. And if we can do that, we can we can save a large amount of energy, and which in turn have positive effects on environment. However, the problem comes here in the experimentations when you try to design the catalyst for such applications, or in any other application, you are going to work on a trial and error kind of experimental approaches. And while the computational methods are, I mean, with the increase of computing resources, they are becoming really powerful tools in this scenario where you can pass the information to experimental team to design nanomaterials at the nano level and can atomically tune the properties actually. So this is the three-step process, as I said, that you have to capture, you have to extract, and convert. And the issue lies in the fact of that the second and third steps is a highly energy extensive, and one needs to reduce the cost and energy for these steps, because if you are giving energy in this extraction and conversion, then there is no use of working on CDU, carbon dioxide utilization, because in any way you will be uh, you will be giving energy and means the money from your pocket to perform these kind of things. So the goal is to design materials which can convert CO2 at normal temperature and pressure. So here comes the role of computations. Actually, we have to design the catalysts, and then the major issues in the catalyst domain is the activity and selectivity, and we have to work towards the improvement in the rational design of catalytic systems. So one of the most accurate technique, as I will be defining, uh, is the DFT, where we work on with the ab initio approach, and that helps to understand the surface phenomena at the atomic level, and we will be mainly using DFT calculations results in this presentation. So if you look at the broader picture in this application, the first step involves atomic scale structural model, and they're predicting the elementary steps in the reaction mechanism, and these are mainly the electronic structure calculation that we will be discussing in the lecture. And then there are other models in this line, which is like uh, once we have these elementary steps formation energies, reaction mechanism, and the pathways calculations, you can fit these elementary steps into the Monte Carlo simulations. And of course, you have to include the effect of local environment. That's the third step, which is sometimes necessary to predict the accurate scenario in the experimentations. And one has to look for the inhomogeneity in the temperature and the reactant concentration as well. So these are the whole scenario in case of modeling the experimentations in the catalyst domain. So DFT, microkinetic models, coarse grain models, and then heat mass transportation models. We will be focusing, as I said, that on the first principles. First principles, they are so strong methods, and the advantage here, the beauty here, whatever I'll say, is that they are not deduced from any other assumption or experiments, as the name said. So we start from the beginning. We do not need any kind of experimentation inputs to start our calculations, and just basic information regarding our system, that on which system you're going to work, atomic number and atomic positions to start our calculations. So, I'm not going into the detail of formalism at the moment, and then this talk, as I said, will be focused on showing you some case studies where first principle methods have shown really nice results, insights. And so, the first detailed analysis I'll be presenting on the copper oxides. And the reason why we choose the copper oxide based materials for such application, because if you look at the literature, there is only one metal which is copper. Copper can produce large number of hydrocarbons, but it suffers from some serious issues, as I mentioned here, the limited energetic efficiency, and the electrode of copper rapidly lose their CO2 reduction activity. So if we can have the copper particles, I mean electrodes with the copper particle like the sides, but they differ from the pristine polycrystalline copper. That was the main uh, goal here. And literature also helped us in that direction. So if you look at the oxidized copper, they perform well compared to the pristine copper electrodes. As I mentioned here, I mean they have shown the increased methanol formation on the oxidized copper compared to the clean copper, and that was the reason. And there are few literature in this domain as well, which shows that increased CO2 to methanol conversion on the copper oxide surfaces. So we thought, okay, let's start the copper oxide first, and then we will do some materials engineering on such kind of surfaces and try to understand it. So, but there are some issues when you try to model the oxide, specifically the transition metal oxides. So the challenge for modern electronic structure methods is due to the inaccurate description of the electron localization within the standard DFT calculations. So, and that is the well-known problem of the pure DFT calculation. There is not exact description of this electron localization. And this is mainly due to the self-interaction error for the DFT. When you try to write the Hamiltonian, you include the electron as well, and you have an extra energy because of the interaction of the electron, which we are talking about, and the other electron gas that we consider in our model. So that is the main issue when you deal with the systems where you have more free electrons, and which we require for the catalytic applications actually to make any kind of reaction on the surface. And also, there are a lot of research now which says that if you calculate the absorption energies from the DFT, plain DFT, you will have some different energies actually compared to the inclusion of the U parameter, which Hubble U parameters in our model. So let's take some basic examples. Copper oxide is a monoclinic crystal, and it is modern insulator with a band gap of electron depending upon how you synthesize and measure the things. And it's a magnetic material having some known magnetic moment. But when you model it with the first principle based simulation pure DFT, GZA approach or LDA approach, we see that it's a metal with no magnetic moment. But when you include the higher level of accuracy in the models, you will get the exact results. So that is the system. So we did the calculation with the TFT, and as you can see here on the center, the dotted line shows the Fermi energy, and you will see that there's some finite number of states crossing the Fermi level. That is the results from the pure DFT, and that is the reason it predicts that it is a zero band gap material. And no magnetic moment as well. As you can see here that we found, yeah, we found that this is a zero, and otherwise the other things were quite okay. And we also find zero magnetic moment in our calculations. So that is the reason, I mean, it was well known, and then that is the reason that you have to go for the next step by including the U parameter correction in your model. And this is empirical method. You have to fit it to the experimental data. And that's how we did. We increased it from 0 to finite values in small steps. As you can see here, at at u equal to 4, you have band gap in the material, and once you have the u 7, you have the experimental range band gap. Oh, okay. So, uh, as our aim is to work on development of catalytic materials, and once you have the catalysts, you have the water, you have the hydrogen, you have the CO2, and any other kind of molecules on the surface, and they're thrown to the environment as well. So what will happen? You will not be able to tell exactly what is the oxidation states of copper oxide. Actually, it's whether it is copper one or copper two. So that means the one is not sure, and this is really challenging in terms of experiments that people really don't know whether they are going to work on copper one or copper two oxides. So as a result, our models should be capable of predicting the accurate properties of both the copper oxide, whether it's a copper 1 or copper 2, CuO or Cu2O. If you look at the copper 1 oxide, Cu plus oxide, you have a unique structure lattice parameter, you have finite band gap, and this is how our result uh, are for EGA plus U calculations for copper 1 oxide, and they're matching considerably good with the earlier calculations. And why we have a very underestimation of the band gap here, because the GGA plus use should not be actually used for the fit to fit the band gaps, except in the case where you have the valence band, the VBM and CBM are the same localized orbit. So and that's the case of the modern insulator in case of CuO, not the case of Cu2O. So that tells you story why this is some um, bad match between the experimental and the computational results. Anyway, so that's the concise slide regarding what we did here. We used the DFT plus U methodology. We varied the band gap, and we found that okay, at some U value, so 7 here, 7 neutron volt, we experimental range for the band gap. We were doing good in terms of predicting the magnetic moment as well. And this is the now electronic loss at this particular Hubble parameter. And we were happy that, okay, now this model is good for both the copper 1 and copper 2 oxide. And that I will show you in the next slide. And these are the other materials. For this particular previous calculation, we used WASP, but we can use the quantum espresso as well. And PBE, GJ calculation. This is how we calculated the surface energies, because uh, I'll come to the surface energies and surface things as well later in the slides. This is how you general formula for calculating the adsorption energy of particular molecule. In case here it was CO2. We used to code metadice for surface reconstruction, and I will be giving you that some detail about why you need the surface reconstructions in this kind of work. And that time we used DFT-D2 method. We can use the other methods as well for van der Waals interactions. Actually. So this is the match between the experimental and computational result. So once we are happy that our model is accurate enough to predict both the copper oxide, we started using CO2 molecule and doing the calculation, but we'll come to this point later. First, what I thought I should be giving at least a glimpse of why you need surface reconstruction and what is the importance of doing such kind of things. So it basically, this was explained by Tasker. You can have different kind of surfaces. Let me go to the next slide, which will be giving a pictorial representation. So, like, look at this. You can have a type one kind of surfaces where you have positive, negative ions. These are the non-polar, because you have an alternate kind of ionic cations. And here in type 2, you have a charge planes where the repeat unit is neutral. So as a total, you will see that the repeat unit is neutral. It is minus 1, plus 2, minus 1, minus 1. So as a total, you have no dipole moment. But look at the type 3 kind of surfaces where you have minus, plus, minus, plus. As a total, you have dipole moment, some direction, which is normal to the surface. And these are the surfaces which are unstable, or you can call them as a polar surfaces. And for such kind of surfaces, to be the case, you need to catch the internal dipole moment, and that's how you can do it. You have to reconstruct it by removing some ions from the top of the surface and adding at the bottom. And in that way, you can break the directionality in such kind of surfaces. Anything, like magnesium oxide, copper oxide, any kind of such kind of used surfaces exist, and while modeling, you have to reconstruct them because these are not going to occur in our experimentations. And before I go into technical results, there are other few things which are important. Usually, we try to calculate the work function, and as you know, that there is a minimum energy required to remove an electron from the bulk of a material to surface to a point outside. So we will do the calculation for the work function. If it matches, we'll be happy. And we'll be using the nudge elastic band calculations for finding the transition state calculations. So you start from the one reactant, you go to the product, and in between you create number of images and relax them by adding the similar force constant between them, and then you find out the exact transition state by calculating the phonons, determining the single frequency instability in a particular direction where you are going to expect your reaction to go. So more results. We started from copper 1 oxide, and we looked at the low index surfaces. They are easy to construct actually. And if you look at the different kind of surfaces, 111 or 110 or 1 surfaces, they can have different kind of orientations. And we started from the exploring different possible terminations. And as you can see that the surface energies are varying, and 111 surface with the oxygen termination is having the lowest surface energy. So based on this, we plotted the morphology. We'll show you that how good they are matching with the experimental results as well. And as you can see here, the takeaway message from this slide is the 111 surface with the oxygen termination. As you can see here, oxygens are more exposed compared to the copper oxygens. Are red ones, copper are the blue ones. So they are most exposed. So we are talking about this particular surface. And then if you look at the surface energies, and this is reflected in the morphology as well. So this is 111 dominant plane is the most dominant planes in the morphology of copper 1 oxide nanocrystal. And then the other things you can see here that our calculated band gap matches well with the experiments. So we were happy. And similarly, we did calculation on the second oxide, copper 2 oxide, O, and we looked at the direction of the magnetic ordering as well. This is a bulk material, and you can have the bulk-like magnetic ordering. You can have line by line, as you can see here, all up, down, or you can have the layer by layer. So all these you have to work on all the possibilities before you can start the calculation for the catalysis applications or any other applications. These are different low index surfaces. We investigated different terminations as well, as I have tabulated in the next slide. So these are the results on the copper oxide surfaces. As you can see here, that 111 surface was much stable, having the lowest surface energy is giving you the test band absorption energy for the CO2. While if you look at the other surfaces, they were having the high surface energies and are giving the more activation for the CO2 molecule. And this is quite obvious actually, the surface chemistry. If you look at that, if the surface is very stable, it will be least reactive. And if the surface is not stable, it will be highly active for the molecules. We further quantified the nature, and as you can see, there are, as I said, that I will be highlighting the markers. So there are markers. For example, as I mentioned in the earlier slide, CO2 activation is represented by how the CO2 molecule remains linear or it's bent. So that's one of the thing. Second thing that what you can do is calculating the phonons vibrational modes as we did here. So if you compare the isolated CO2 molecule vibrational modes with the one which were activated here, you will see that there is a difference between the frequencies. And as a result, we can say that CO2 is activated here. The second thing that what you can do here is, of course, looking at the structural deformation here at the surface level. And the thing which I'm highlighting here is the charge density difference plots, beta charge analysis. So all this will give you an idea whether okay whether your surfaces are activating the CO2 or not. So well, uh, our work is not done yet. We were targeting to convert CO2 into some chemical fuel, and this is how the next step is either. So look at this left side calculations. Try to first dissociate the CO2 molecule. The CO2 molecule was having a bond here on the upper side of the copper oxide. And we tried to dissociate it and doing the calculation, attaching the oxygen on the various sites available here. And this was the most feasible one, the one at the corner of our unit cell. And if you look at this value is suggesting you that, okay, this is not going to happen. So that the activation barrier came here to be really very high. And that is the result of we did not proceed in this direction to further convert into carbon monoxide into something. And then the only option left was to identify the the source of hydrogen. So anyway, if you're going to convert the CO2 into methanol, methane, or any other product, you need hydrogen source. And hydrogen source can come from the two particular options here. One, either you can dissociate the water molecules over the surface. So this is the water molecule attached or the opposite, and then I try to dissociate, and the calculation shows that okay, just you need zero point 0.2 electron volt energy to dissociate water molecules over the these 111 surface. And the similar kind of results we found for the hydrogen. These are the hydrogen gas molecules, and the similar kind of results we are seeing here that you can have the atomic hydrogen on the surfaces either from the hydrogen gas molecules dissociation or water molecule dissociation. So now you have the CO2, now you have the atomic hydrogen. What is next? Next is to look at the kinetics towards formation of some products. So let's start from here. You have CO2. Let me again explain the color coding here. These are the surfaces of copper oxide. You have red color balls as representing the oxygen of copper oxide and blue as a copper. And then distinguish between the oxygen of the CO2. We have marked them with the green color. So this is the CO2 molecule, and this is hydrogen in the gray color. We found that you can have two kind of configurations. Either you can have the hydrogen here or here. And in both cases, let's now try to attach the hydrogen to somewhere to CO2. And that's what we did. There are two options here that I will be highlighting. One, this hydrogen comes and close to CO2 and attaches to one of the oxygen of CO2 molecule, which you call it as a carboxyl, HCO. So we tried to, I mean, this is really compute extensive calculations, but in a few seconds I will be convincing you that these are really powerful tools in the catalytic science. So if you look at the transition pathways, finally we found the carboxylic acid can be formed. However, look at these barriers. There's a really high energy extensive barrier, and you cannot do such kind of formation in the lab. I mean, you can, but you have to spend a lot of money from your pocket. However, there is another option. Another option was that hydrogen, this atomic hydrogen connects with the carbon. And that's the second option the chemists people have in such kind of reactions, which we will be calling it as formate. So now just ignore these steps. Look at the formate. So for formate to form, you just need about 0.14 electron volt energy. That means in no time you will be getting going towards this particular reaction, not the one of carboxyl. So in a one-line summary, you will be forming the formate over copper oxides. And once you have formate, no time you will be having the formic acid formation on copper oxide 111 surfaces. So these were the results explaining how these copper oxide-based surfaces, nanoparticles, are good for the formic acid formation on the room temperature. We'll be going now towards the engineering the materials for the uh, activation of CO2. And there are various methods actually. The one which is these are the methods people have been using, attaching the surface molecules, or one which I really like is the defect engineering. You can substitute, or you can do the strain engineering. In our lab, we are doing all the things on different materials, as I will be showing you in the next few slides. So we worked on the vacancy creation on the copper CO111, and as you can see that once you have the vacancies on this kind of copper oxide nanoparticles, the yeah. So once you have vacancies, you have the better the binding energy from -17 or so. It's increases to about 90 kilojoule per mole. So that's the way you can activate the CO2 on more these kind of surfaces. Now, these are all the results that we presented were we published it, and these were basically simulation result. And people are very curious actually that okay, how does it compare with the experiments? So I will not be going to detail of how our models matches because we did it. We found it reasonably good match with the bond distances and the lattice spin distances experimentally in the same time images. But let's look at the product formation thing. So this is the drift analysis results from our experimental colleagues at University College London that time. And what they did, they started from CuO nanoparticle here, and they bombarded the hydrogen gas in the chamber, and they had two observations here. The one, as you can see here, that after some time, the CuO was reducing into the Cu2O and finally into copper. That was the first observation that they found here in the experiments. And the second, as you can see here, in terms of products that they found, was that they did not find any methane or the monoxide. They found the formate formation, and you can see the segment pink colored um, peak here. And that was mm, somewhere in between when they had this uh, Cu2O on the as a nanoparticle. So they were puzzled actually that what is happening here, why this copper oxide nanoparticle were reducing from CuO to Cu2O and then finally to copper, and why only formate, not any other product actually. So this was the I mean, you cannot have the insights from your experiments, the observation that you can have. But insights you can have from the first principle relations or first principle based other methods. So we did the calculations here. We started from the CuO pristine 111 surface. And from the one image, you will be able to understand why the things were changing from CO to CO2. Look at the surface here. You have a copper, oxygen, pristine CO surface. And as soon as you place the hydrogen in your model from the first principle DFT calculation, it will convert it into the lowest energy state. And the lowest energy state was formed when one of the oxygens detaches from the surface and forms water molecule, surface bound water molecule on the copper oxide. So what exactly happening here is you are reducing, I mean, there are two things happening. One is this hydrogen molecule is interacting with the oxygen. Yes, okay. But what exactly is happening here is you are reducing the surface. You are reducing the copper oxide. So means CuO is getting converted at some point to Cu2O, which was happening here. More and more hydrogen, more and more oxygen will um, bond with the hydrogen molecule to form a surface bond, water molecule over the surface, and that's what our experimental partners found in their experimentations. So the one puzzle was solved here, that why this guy was reducing to this, and finally copper electrode. Second, why copper? Why? So I think this we already discussed in the few slides. If you don't remember, let me just show you the again the same things. What we found that once you have the CuO, difference oxide 111 planes, in no time you will be having formate and formic acid on your surface. Actually. So that was I mean, this was published earlier, and that's the whole story was clear here with the help of experimentation. So that's how we in these simulations are really powerful, though they are at room temperature, but still they are so much powerful that they can explain the atomic level reaction mechanism in even such complicated catalytic reactions. So again, coming to the same defects in the engineering in these materials, and we'll be showing you some cases where we are working on the defects in engineering and found that CO2 can be activated. We have okay, so we have been working on the 2D materials as well from past few years, and as you know, Maxine is one of the newest in this domain. You have conditional carbides, nitrides, or even carbonitrides. They are having applications in different domains, and we were interested here in the catalytic applications. And there are some methods. You have max phase, you do etching, and you can create the maxine. So we will not into this, and we will first discussing you the few two things here. We have recently been working with one of two of our students who are working on this domain, Archana and Kamal, on PIVC vaccines, and we have been working on the gas sensing and CO2 stuff on these molecules. And as you can see, this one is CO2, and they are the future job molecules here. So what we thought that okay, let's do the defect engineering here, and we created. We tried to link with our earlier work in this area in 2020, where we worked on some other vaccines. We'll be discussing M2 TIC2 takes vaccines. So that is the plan here in case of TIVC as well. Let me show you some fascinating results on this. So what we did here, I mean, we tried to design defects on these vaccines, and we explored all possibilities here. This is the pristine vaccine, and here the vacancy for titanium, molybdenum, and here we removed two molybdenum atom. Here is a two dual vacancy here, and here one molybdenum and one TIA. Just a second. Yeah. So further did we further did the calculation in this direction, and as you can see here that you have the perfect Maxine's states here by black, and you have the vacancies states introduced in our system, and we calculate the formation energies. We'll not discuss much about these calculations here. We'll be focusing on the CO2 activation things here. And one of the important parameters is the electron localization function. And why they're important, let me tell you. If you look at a definition point of view, it will be give you the qualitative understanding of the electron localization and behavior of electrons over the defective surfaces. So this is the ELF plots for our Maxines here for different kind of defects, and you can see here that electrons are localized on different domains close to the defects uh, and close to defects as well as the functionalization groups. The dashed circle lines highlight the place of removed atoms here. Now, once you have idea of where are electrons here through the such kind of plots, so you have you I mean, these are electrons are completely localized over the place of removed oxygen atoms or vacant vacancies. So based on the ELF analysis, we place CO2 molecule close to different sites on the monolayer and in different orientation, and we try to look at how CO2 is binding sites. So these are the perfect vaccine, and these are the scenarios over the defected ones. If you look at the results, you have the variable binding energies in case of defects, and the molecule is highly attracted by the defect found on a single MO atom vacancy. Moreover, there are different results on different kind of vacancies here. We have been working on similar kind of 2D materials, and these are the heterostructural materials which we designed few years back, and we are working on the CO2 stuff as well on these materials. So what we did, we mixed the graphene site with the 2D gallium nitrides by replacing half of the equivalent of carbon atoms with the gallium and nitrogen, and we give insights regarding what kind of heterostructures you can have in your experimentation. We calculate the formation energy, which came out to be negative, which says that okay, you can have the such kind of structures formation. Similar kind of results were indicating for in case of boron nitride and gallium nitride 2D structure. These are 2D band gap materials, direct band gap materials, which can find applications in various domains, including optoelectronic materials. We have been working recently on graphene, which is 5, 6, 7 carbon rings. And as you can see here, you have 5, 6, and 7 member rings. And we first did the hormones and the structural calculation to look at the stability of such kind of surfaces. And these are the technical details. I will not go into detail, but we'll be focusing more into the CO2 step things and defect engineering. So these are the PDOS and bands for the pristine graphene, graphene, and graphene. And if you are quickly wondering what is graphene, graphene, and graphene, let me go you back again in the first slide. So this is the side graphene, but if you hydrogenate it on the one side, you will see this, the graphene, and if you hydrogenate it on the both the sides, you will have a graphene. So look at the CO2 results here. If you look at the binding energy, these are the and the results on the right side. You will see that these are the very weak feature jobs occurring in such kind of materials. What we did here again in the next step, we worked on the one of the method where people have been working on the single atom catalyst, or you can see that the decoration of the 2D materials with the transition metals towards CO2 activation. And you will see here that once you decorate such kind of materials with the copper single atom, you have for case of like graphene, the binding energy increases to about um, 3 times to the original ones. These are the further quantification of the results where we have worked on the charge density difference plots and uh, yeah. So this is towards the vacancy creation, and again, if you will see that if what we did here, we removed one of the items here, mono vacancy and other vacancy here creation. We created the formation energies here, and we have been working on the strain engineering of these materials as well. And you will see in some cases, after some particular compression strain, you have very huge activation of CO2 in such kind of molecule. And we did the Phonon calculation on these strained molecules as well, strained structures as well, and we found the structure, we found that the structures to be very much stable. We have been working on the 2D metal oxides as well in this direction, and my lab is really thankful to the Materials Square for providing the grant last year. Our group was selected as one of the top five research groups around the world for performing for using Materials Square platform, and we um, managed to do very nice fast calculation on the platform. And this is one of the projects which is in the publication stage on the copper oxide 2D materials. I'll be quickly showing you some other results as well in this direction. We have been working on other 2D materials as well, and specifically BCN materials, which we did in collaboration with the Professor Sienna Rao's research group at GNCS Bangalore. So here the aim was to mix graphene with the boron nitrides and mix and find out what kind of ordering you can have or what kind of ordering you have in such kind of structures, what kind of uh, electronic nature they will be having, surface energies, and how they will behave to the greenhouse gases absorption, CO2 activation, and all. So let's quickly move on. So the first task was here to how does the boron nitride decorate the carbon lattice? And that's what we did here. We tried to mix them in all possible ways. And what we found that this was the lowest energy structure having the CN and BC bonds at the interface. While the one which were having the BN and BB and NN bonds were the having the highest energy means least stable. So the second step, what we did in this direction was to look at the effect of increasing the domains of graphene in the boron nitride lattice. So if you have more bigger domain of graphene in the boron nitride lattice, your structure is more stable. So that's a thing we can conclude here. You have the different electronic structures by mixing the different in different concentration, different configurations, and bigger the domains of your graphene in the nitride, or vice versa, you have the better stable materials, and you have the tunable bandgap materials in this direction. Some details about the electronic structure calculations, frequencies, some rippling was there. So that all depends upon how you can tune the domain sizes and can increase the stability of your structures. We have exploited them experimentally as well as the computationally. I mean, my group computationally, but in collaboration with the experimentations of Professor Rao's group at Bangalore towards the greenhouse gas absorption. Uh, so let me just quickly go to the experiment, the computational part. So this is a BCN single unit cell. We placed CO2 molecules over different kind of sites you can have, and we started from the one CO2 molecule, as you can see here. Left one is the BCN, right one is the graphene, and these are both are field absorption, no chemical activation here. And if you look, if you compare with the graphene, we found better absorption here in terms of binding energy as well as the interaction distance. So CO2 binds more strongly, and then we increased the concentration and identified how much maximum weight percentage uptake you can have on BCN as well as on the graphene. So once you have more and more molecules, you see repulsion. Even if we repeated the calculation by increasing the size, so supercell size as well, and we found the same weight percentage here on them as well. Similarly, I mean, I will be skipping this methane interaction. Overall, what we found that BCN seeds are better than the graphene seeds for such kind of applications, and this is how we predicted the maximum uptake for CO2 and methane on BCN. And this was highlighted as one of the hottest article in Campus Chem in organic chemistry. So let me summarize what we are doing here. We are working on various computational techniques, mainly on DFT, but we are also working on QMMM and machine learning approaches for materials design. We are working on various applications, though we have in this talk I have focused on CO2 capture and conversion, but we have been working on gas sensing in collaboration with the University of Kiel, Germany, thermoelectric materials, and battery materials as well. And we have some funded grants here. I would like to highlight the one here from the last year from the Materials Square. And we have some Indian government funded projects in this direction as well. And these are different applications. So this is the work which I would like to highlight. We have been working on the battery materials, 2D materials structure for battery electrode developments. This is the CO2 capture and conversion that what we discussed, and one of the domain in which our group is working on the metal tetrapods designing for efficient gas sensor materials design. And recently we have been working on the ML-based approaches towards the photovoltaic material development. One of my student, Anjali, is working in this project. Before I close, I would like to acknowledge my PhD students working on these various projects. And thanks to funding agencies, the UPES for the seed grants and PhD fellowships to students, University of Kassel and University of Southern University of Denmark for the computational resources and visiting scientist positions, SERB, DST for Indian government for the grants, and Materials Square for the computational resources last year. Thank you.